Hello guys, in this lecture we'll be studying the topic quadratic equations from mathematics. It's one of the fairly easier topics for JEE preparation. First we'll be going through some important points in the theory involved for quadratic equations, and then we'll be going through some questions. Let's start.
First of all, we define our equation to be f of x is equal to y. Let this be a quadratic. Now we'll look at some properties of this. Firstly, we define the thing domain. Domain is a set of values that x can take to put into the function, and range is a set of values that y can take.
Right.
In the function. Again, we know the difference between a relation and a function. In a function, x can basically the difference between a function and a relation being this is a function while this is a relation. That is, for one value of x there can be only one value of y. That is called a function. Here we see that for one value of x there are two values of y. So this is a relation and this is a function. So here quadratic equation is also a function. Here we'll be dealing with quadratic equations. So if you define a quadratic equation to be ax square plus bx plus c equal to 0 and let alpha and beta be its roots, then suppose a, b and c belong to R. A is not equal to 0 because
R is the set of real numbers.
Exactly, because if a is equal to 0, the equation will be linear. Then we define alpha beta to be minus b plus minus root b square minus 4ac by 2a.
And this is a very important formula.
Exactly, where root b square minus 4ac is the discriminant. Next we come on that the sum of roots, that is alpha plus beta, is minus b by a, and the product of roots alpha into beta is c by a. And also the quadratic ax square plus bx plus c, we generally write it in the form a into x minus alpha into x minus beta. That is, we write it in the factorized form of its roots so that doing its analysis gets easier. Now we define let S be the sum, that is alpha plus beta, and P be the product, that is alpha into beta. And if we are just given the roots, then also we can determine the quadratic equation because it is x square minus sx plus p equal to 0. Next we look at the nature of a quadratic equation. The discriminant actually defines the nature of a quadratic equation. There can be three cases, the discriminant being less than 0, equal to 0 and greater than 0. If it is less than 0, the roots of the quadratic equation are non-real, that is complex roots.
And they are conjugate.
Exactly, most of the time they are conjugate, that is of the form a plus minus b iota. Secondly, if discriminant is equal to 0, then the roots are real and equal, and the equal root, its magnitude is given by minus b by 2a. Obviously, if d is equal to 0, then we can put this value in the formula we determined above. We can see the answer will be minus b by 2a, as this term will tend to 0. The third case being the most common one, if the discriminant is greater than 0, that is, then the roots of the quadratic equation are real and also unequal.
Right.
Here in our syllabus, we'll be mainly discussing with the second and the third case, that is the discriminant is greater than or equal to 0. Next point is that if a quadratic equation in x has more than two roots, then it becomes an identity, and also a is equal to b is equal to c equal to 0 in that case. Obviously, because a quadratic having degree 2 is supposed to have two or less than two roots, but if it happens to have more than two roots, then it becomes an identity, that is, it is satisfied for all values of x, and in that case a equal to b equal to c equal to 0. Next, we discuss about the graph of f of x, that is the quadratic. The shape of the curve f of x is equal to 0 is always parabolic. There can be two cases. We determine a quadratic first of all in the form a into x minus alpha into x minus beta, factorizing in terms of its roots. In this case, if a is greater than 0, then the parabola is open upwards, and if a is less than 0, then the parabola is open downwards. That is, if we define these can be two possibilities of a quadratic. If a is less than 0 or a greater than 0, this is a greater than 0 and this is a less than 0,
right.
This being the x-axis.
So in the case when a is greater than 0, we have a minimum value for the quadratic equation.
We have a minimum value,
and we have a maximum value for a less than 0.
That's right. After that we come on to when the case when the quadratic intersects with the x-axis. There again arise three cases, first being d greater than 0. For that case, we know that the parabola cuts the x-axis at 2 points, that is, it has two real and unequal roots, and the points of intersection being the roots, that is minus b plus minus root d by 2a, and a graph being of this form, this being the x-axis, and these being the two roots, that is alpha and beta.
Right.
After that, we define if d is equal to 0, then the parabola touches the x-axis in one point, and the point of intersection there is determined, that is the only root, that is minus b by 2a. The parabola can be this way for a greater than 0, just touching, or this way for a less than 0.
Right.
The last case, if d is less than 0, the parabola doesn't cut the x-axis at all. Whenever the parabola touches or cuts the x-axis, the number of roots is equal to the number of times the parabola touches or cuts the x-axis. If d is less than 0, the parabola doesn't cut the x-axis at all. That is, our graph will be either like this or like this, depending on a greater than 0 or a less than 0. Next, we define v if to be the vertex of the parabola. In that case, the vertex is determined by minus b by 2a comma minus d by 4a, where minus b by 2a is the x vertex and minus d by 4a being the y point.
Okay.
Line passing through the vertex and parallel to the y-axis is known as the axis of symmetry. That is, if we define our parabola to be of this form, then this is our vertex, that is minus b by 2a comma minus d by 4a, and this being the graph for a greater than 0 and d also greater than 0. These being the two roots, that is alpha comma 0 and beta comma 0. This is our axis of symmetry. Next, we come to the maximum and minimum values of the quadratic f of x. We say that f of x has a minimum value at the vertex if a is greater than 0 and the value is minus d by 4a. That is, the minimum value is minus d by 4a and it is at the point x is equal to minus b by 2a. That is, in case of this graph or this or this, in all these cases the minimum value is always x is equal to minus b by 2a, is at x is equal to minus b by 2a, and the value itself being minus d by 4a.
Yeah.
This is for a greater than 0. We have a maximum value of the quadratic if our a is less than 0 and its magnitude is minus d by 4a and it occurs at x is equal to minus b by 2a. That is, it could be this way. There could be many possible cases for this. In all these cases, this being the maximum value. Next we come, this was all about quadratic equation. We talk about quadratic inequalities now. Again, let f of x be ax square plus bx plus c. After that, we again take many cases. The first one being d greater than 0. Remember that in all these cases, firstly, we take a quadratic to be of the form a into x minus alpha into x minus beta. For simplification, we just factorize into the form of its roots and take a common. Now, the first case arises that d is greater than 0. In this case, if x minus alpha into x minus beta is greater than 0, then we say that x belongs to minus infinity to alpha union b to infinity, and make a point that since equality doesn't lie in the comparison sign, we don't have a close bracket anywhere. So thus we could represent it as, if these being the points alpha and beta on the axis, the line that we are drawing is the range of values of f of x, is the domain for our x. Second case is if x minus alpha into x minus beta is greater than equal to 0. In this case, x will belong from minus infinity to alpha union beta to infinity, where alpha and beta have closed brackets. That is, our x could also take the values alpha and beta in this case, and since it can take the values, thus we represent it by the closed dot, and in earlier case we represented it by the open circle. Third case being when our x minus alpha into x minus beta is less than 0. For that case, x lies between alpha and beta, again not including alpha and beta since equality doesn't lie in the comparison. Fourth case being x minus alpha into x minus beta is less than equal to 0. For that case, x belongs from alpha to beta, including both of alpha and beta, that is we represent it by a closed dot. Now these were the cases for our d to be greater than 0.
Okay.
Next we come on to a second case where d is less than 0, and if d is less than 0 and if a is greater than 0, we say that f of x is greater than 0 for all x belongs to R. This is quite logical, as we know that if d is less than 0, our graph, our parabola won't cut the x-axis at all. Therefore there can be two cases, and also it is given that a is greater than 0, hence there could be the upper one case only.
Right,
so we see that f of x is always greater than 0 for all values of x.
Okay.
It can't lie below the x-axis. Similarly, if a is less than 0, this being the first case, the second case, if a is less than 0, the graph will always lie below the x-axis. Therefore, f of x is less than 0 for all cases, for all values of x.
Okay.
Similarly, we can see the other four cases, that is if d is equal to 0 and a is greater than 0, we know that on our graph the parabola will touch the x-axis. So we see for d and e case that the d1 being this way and the e1 being this way, thus touching the x-axis.
Yeah.
Thus f of x will be greater than equal to 0 here, and f of x will always be less than equal to 0 here. Similarly, we can see the f and g cases, that if d is less than equal to 0, we see and a is greater than 0, then we say that f of x is greater than equal to 0, and if d is less than equal to 0 and a is also less than 0, we say that f of x is less than equal to 0.
Yeah.
Next we come to a topic, the maximum and the minimum values of a rational function. We define a rational function as f of x is equal to y, that is y is equal to ax square plus bx plus c. So here we see where x belongs to R. We find the maximum and the minimum values of x depending on the following cases. Obviously we know that let there be a case where y belongs to a to b, that is if this is being a and b, y can take values both including a and b. In that case, we say that the maximum value of y is b and the minimum is a.
Right.
Second case, if a belongs to minus infinity to close bracket of a, union close bracket of a to infinity, we say that the maximum value is not defined and the minimum value is also not defined, as you can clearly see that thing from here. Third case is if y belongs to minus infinity to infinity, that is we say that y belongs to R. In that case again, the maximum and the minimum values of y are not defined. We would see a greater use of rational functions in the questions that we discuss later on. We next come to the topic, the positions of roots of a quadratic equation ax square plus bx plus c equal to 0. That is, we say that we determine the position of the roots compared to any two given numbers k1 and k2. For that, we see the first case, that is we see if a number k lies between the roots, that is let alpha and beta be the roots of the quadratic equation, and we say that a number k lies between the roots, then the condition for that should be a into f of k is less than 0, where we know obviously f of x is equal to a into x minus alpha into x minus beta. Secondly, we say that let there be two numbers k1 and k2, we say that if both k1 and k2 lie between the roots, that is let the roots be alpha and beta and k1 and k2 be two numbers, then we say that the first condition to be satisfied is a into f of k1 should be less than 0, and secondly a into f of k2 should also be less than 0, both at the same time. Third, we see that if a number k is less than the roots, that is we say let these be the roots alpha and beta, and we define a number k that is less than both the roots, then we say that firstly d is greater than equal to 0 for that, secondly a into f of k should be greater than 0, and thirdly the number k is less than the vertex point, the abscissa of the vertex point, that is it should be less than minus b by 2a. Fourth case, we see that if a number k is more than the roots, that is let these be alpha and beta be the roots, and the number k is greater than both the roots, in that case the discriminant will be greater than equal to 0, and secondly a into f of k should be greater than 0, and thirdly the value of k should be greater than the vertex point, the abscissa, that is minus b by 2a.
Right.
The fifth case, we see if both the roots lie between k1 and k2, that is let there be two numbers k1 and k2 and let the roots alpha and beta lie between these numbers. For that case, firstly, the discriminant should be greater than 0. Secondly, a f of k1 should be greater than 0 and also a f of k2 should be greater than 0. And thirdly, the vertex point, that is minus b by 2a, that should lie between k1 and k2 depending on which is the smaller and the bigger number.
Right.
Last case, we see that if exactly one root lies between k1 and k2, that is, let there be two numbers k1 and k2 and here lies alpha, beta could be here or here, or then we say the condition to be satisfied is the product of f of k1 into f of k2, that will always be less than 0.
Yeah, but we don't really need to remember these formulae. It's
Exactly.
quite intuitive. As in, if you know the basics, if your basics are clear, and you can easily draw the roots and the numbers on a number line and derive all these conditions very easily.
Exactly. We just need to be good with the visualization of the graph portion of the
Exactly.
quadratic equation, which we'll also see further in coordinate geometry. If that is clear, these equations, these conditions are actually very easy to memorize, but we still note them down in a place, so just to save time.
And the application will become clearer when we go through the questions.
In more difficult and complicated questions. Next, we see that if both the roots of f of x is equal to 0 are to be negative, that is less than 0, then we say that minus b by a is less than 0, firstly. Secondly, we say that the product of roots alpha and beta, that is c by a, is greater than 0, and thirdly, the discriminant has to be greater than equal to 0.
Because the roots
Exactly.
exist.
Since the roots are negative, so obviously they are to be defined in real, and so discriminant should be greater than equal to 0. And obviously we know that the product of roots is greater than 0, because if both are negative, so obviously minus and minus will become
Make it
positive
positive,
again.
yeah.
Exactly. And since both the numbers are negative, so their sum will again be less than 0. So again, we don't need to memorize it. It's really logical thing. Next, we see that if both the roots are positive, for that case, b minus b by a, that is the sum of roots, that should be greater than 0. The product again should be greater than 0, and the discriminant should be greater than equal to 0. The logic again coming as the previous point. And the last point, we see that if the roots of a quadratic are opposite in sign, we say that the product should, that is c by a, should be less than 0.
The sum can be positive or negative.
Exactly. The sum can be positive or negative depending on which magnitude is greater, of the positive number or of the negative number.
Right.
But obviously the product has to be less than 0, because one sign will be negative and one will be positive. The quadratic equation is basically a topic which doesn't have much of a theory. It basically has more of logical implications that we'll be seeing in the questions. We see here some more results which are related to a cubic equation now. In a cubic equation, let me define a cubic equation as ax cube plus bx square plus cx plus d equal to 0. In that case, we find out that alpha plus beta, let alpha, beta and gamma be its roots. In that case, we see that alpha plus beta plus gamma, that is the sum of roots, will come is equal to minus b by a. Next, alpha beta plus beta gamma plus gamma delta, that is summation of alpha beta, summation of the product of two roots taken at a time, that comes to be c by a. And thirdly, alpha beta into gamma, that is the product of the three roots, comes to be minus d by a. This holds true when our cubic is in this form.
Yeah, and we can generalize these formulae for any power, as in any ordered
Exactly.
equation. Like for let's say an equation with the maximum
power
power
4.
4. The first will be the sum of roots will be minus b by a. Then sum of roots taken 2 at a time will be c by a. Sum of roots
Exactly.
taken 3 at a time will be minus d by a.
Exactly. So if this being a biquadratic equation, in that case the sum of roots will be minus b by a. The product of roots taken 2 at a time, that is sigma of alpha beta, being c by a. Then the product of roots taken 3 at a time, that is sigma alpha beta gamma, is equal to minus d by a. And lastly, alpha, beta, gamma into delta, that is the product, all of them taken at a time, is equal to e by a, where the four roots being alpha, beta, gamma and delta.
Right.
So this was all for the cubic equation. And maximum number of positive real roots of a polynomial equation. Let the polynomial equation to the power n be defined as f of x is equal to a naught x to the power n plus a1x to the power n minus 1 and so on till a n minus 1x plus an. Let this be a equation is equal to 0. Then we say that the maximum number of positive real roots that this equation can have is the number of change of sign of coefficients, that is change of sign of coefficient from positive to negative and from negative to positive. Similarly, we have another result, that is the maximum number of negative roots of this f of x is equal to 0, the polynomial we defined above. It is again the number of changes in the sign of coefficient, but in f of minus x is equal to 0. That is again sign from positive to negative and from negative to positive, but in the equation f of minus x is equal to 0. These both are derived results from the basic formulas we have, but they are sometimes useful when the question is and these results can sometimes be directly applied.
Yeah, they are tricks. They can be used in tricky questions.
Exactly, where otherwise it would become a very lengthy question. Where the powers are high, you could directly use these results.
Exactly.
So basically this was it for the theory of quadratic equations. Now we shall be having a look at the questions of quadratic equation and see some more cases and concepts there.